Hello everyone, this is Changze Lü from Fudan University, Shanghai, China. In this video, we will introduce our ICML paper, Efficient and Effective Time Series Forecasting with Spiking Neural Networks. This work was conducted during my internship of Microsoft Research Asia, supervised by Yansen Wang. Firstly, I would like to introduce the background of this paper. As shown in the figure, the basic unit of SNNs is spike neuron, which is a kind of mimicry of neurons in the human brain. There is a threshold in spike neurons. When the input value is higher than the threshold, the neuron is fired, which can be regarded that the output is 1, otherwise the neuron is not fired. Therefore, we can see information in spike neurons as binary values instead of floating numbers. The input data of SNNs will be converted into time-varying spikes, indicating that there are only binary values in every time step. Here, I show a recurrent representation of a leaky integrate and fire neuron. These are equations that describe the dynamics of the LIF neuron. The ST is the Heaviside step function that is not different bowling. At every time step, ST will decide whether the LIF neuron fires. A very popular strategy is to regard ST as this equation so that we can calculate its gradients. This is a figure that shows how the surrogate gradient works. Then I will introduce the time series forecasting task. Generally speaking, this task is to predict the horizon based on the historical observation. Current methods cover statics-based, CNN-based, RNN-based, and transformer-based, and so on. Notably, the time series also contains the concept of time steps. Therefore, it's a problem that how to align two time steps when we use SNNs to process time series data. So our work aims to effectively and efficiently utilize SNNs to solve this task. Next, I will introduce our method. And this is an overview of the method. It includes two parts: temporal alignment with spike encoders and spiking neuron architectures. Well, firstly, I will introduce the concept of temporal alignment. Similar to previous works on image processing, we think it is necessary to unsqueeze an external dimension for LF neurons to transport spike information. Our key idea is to divide a time step delta t of the time series into TS segments. The representations of our target can be written as converting floating point number with dimension t times c to spikes with dimensions ts times t times c. So to achieve this target, we need a special spike encoders that can not only generate spikes but also maintain the time series information. For previous studies on image processing, repetition for t times is widely used, but in fact, this method will disrupt the continuous nature of time series. So we propose two parametric spike encoding techniques, a delta spike encoder and a convolutional spike encoder. As shown in the slides, these two approaches are quite simple and effective. Then we will introduce how we modify SNNs from classical ANNs. We convert 3 types of ANNs tailored for time series data to their SNN counterparts: TCN, RN, and current SOTA I transformer, which is accepted by ICLR 2024. As well, we also follow these basic rules of ANN to SNN conversion methods. Replace ReLU as LF neuron and SEW, which names spike element-wise residue module, and softmax free spiking self-attention. It's worth noting that for spiking transformer, we choose spike former, which is accepted by ICLR 2023. Finally, I will show our experiment results in this part. For main experiments, we choose 4 classic real-world multivariate time series benchmarks, 2 about traffic, 1 about solar energy, and 1 about electricity. The table shows in the slides is about the features of these data sets. For evaluation metrics, we choose RSE and R-square. Well, in this table, we report all the results. Generally, we find the results of SNNs are mostly comparable to their ANN counterparts. And under certain settings, such as spike RNN and iSpike former, can outperform their ANN counterparts. We also calculate the critical difference of all methods in the above table, and we find that SNNs succeed when temporal dynamics are properly preserved and handled. SNNs with temporal modeling can be further improved by advanced spatial modeling techniques. Then we will introduce our analysis experiments. Firstly, to show our proposed spike encoders are effective, we do an ablation study on spike encoders. Well, as shown in this table, we find that SNNs with repetition encoders may struggle to converge. You can see the repetition encoders leaves many unconverged when training. Both convolutional and delta spike encoders are effective if event-driven spike generators. And 3, shape-based encoder, which takes a wider scope of sequence into consideration, is more effective than a change-based encoder. And secondly, we analyze the sensitivity of hyperparameters, time series t and decay rate beta. We find that the R-square value remain relatively stable with minimal variations as TS increased. And higher beta makes SN more persistent in its internal state, which is beneficial for retaining long-term information. Then we also create synthetic time series data to evaluate our SN models. The 2 following figures shows our SN successfully process both low frequency and high frequency signals, especially the temporal signals. Well, finally, we also conduct an energy experiment. We estimate the energy consumption based on the following equations. Well, these equations notably are based on the assumption that we run our SNNs on 45 nanometers neuromorphic chip. This is our poster. That's all. Thank you. Here are our emails. Feel free to contact us.